Welcome to the session on program verification. We've got 3 talks coming up. The first one, I'm pleased to introduce Marron from Microsoft Research, who's going to talk about high assurance software for financial regulation and business platforms. Mark.
Okay, great. Thank you for the introduction. I'm Mark, and I'm really excited to be here to talk about kind of a exciting collaborative project today. So Stephen and Attila are from Morgan Stanley. Tosha is from the Fintech Open Source Foundation. Earl is actually from University College London, and then I'm from Microsoft Research. And so we've all been sort of coming together across around a sort of an interesting platform and an interesting problem space that we wanted to talk about. And so the space is the financial technology sector is really in the last 5 years has moved from everything is going to be in-house and siloed and proprietary to really embracing open source technology to enable them to streamline and modernize the workflows that they have to deal with. And this is really exciting. It makes it a much easier place to do these kind of collaborative projects in. And it's kind of interesting because they have a lot of problems that we're familiar with or familiar to anybody building software in the industry. So time to market, software, overall software quality, user satisfaction, the amount of developer effort that's required to do something. But there are also some interesting, unique challenges that they have in this kind of transformation in this process. And these are really around like regulatory compliance, auditability, legal liability, right? It's not just enough to sort of write the software, call it a day, and maybe fix some bugs if things come up, right? Just this last year, Citibank was fined, I believe it was $400 million for issues with their data management, quality, and processing workflows, right? So it's not enough to just, get the right answer or get unanswered. You really want to have confidence that you're doing the right thing, and you want to be able to explain why you believe you're doing the right thing. So this is kind of a great place that, from my perspective, that the formal methods community can really contribute to this transformation. So I mentioned sort of 2 challenges. So one scenario that they have is kind of like an internal line of business application. And this would be familiar to all sorts of software developers. So this is like an application that is a surfboard rental web app. And so you might, we have a flow diagram here that was actually automatically produced from the code. And it goes through and it checks like how many surfboards are requested, how many you have on hand, what the weather is, does some analysis about expected returns, and then decides whether or not you can rent those surfboards. And shown on the right is the actual code that's in that this was derived from. And you can see it's sort of a standard functional language, let-based, pure functions, conditionals, the standard stuff you'd expect from the sort of ML family of languages. Another kind of application that's representative of these regulatory compliance applications is taken from a bit of code that's designed to implement several hundred pages actually of regulations for computing liquidity ratios that investment banks have to maintain in order to be compliant. And when you look at this, it's hundreds of pages of prose and tables and some examples. I was looking through it, and I think they say it is expected to take 100+ hours to gather all the information and complete one of these reports every time you do a report, and the banks are required to do this on a regular basis. So this is kind of the place that is ripe for using software to make this process more consistent and more efficient. And if you look through these regulations and everything, it actually distills down kind of in this figure just a bunch of sort of flow computations and conditionals and switches about different types of assets and summing them up and taking their ratios. And it maps really nicely into sort of this functional flow-based programming paradigm. The code here is shown on the right again. And I think this is a really good example, of a place where it's not just enough to say, we had a GitHub code review and we looked at the code and it looked pretty good, right? You want to be able to go and definitively say, hey, I don't have any code that's producing an infinite number, right? I don't have any code that's rounding the wrong way and producing garbage results. And you want to be able to have this formal confidence as well as sort of a process-based confidence that your code is actually doing the right thing. So there's sort of some exciting examples of what's going on in this space and what we were thinking about. And so in this process, this collaboration came together through a number of entities. So I'm going to mention one is FINOS, and this is the Fintech Open Source Foundation. It's part of the Linux Foundation. And there's actually a subgroup in there across multiple banks that's actually interested in exactly this reg tech space. So how can you move regulations from prose and manual process to a more formal description and code implementations. Another collaborator here that we worked with a little bit is from Goldman Sachs. So they have a language called Legend that they developed internally. It's actually a functional language too, that they use for data integration and governance and compliance. And they just open sourced it a couple years ago. And then the stack that we're going to talk about today in more detail is Morphir, which was developed internally at Morgan Stanley, and again, released as open source about a year or two ago. And we started working, actually, the Morgan Stanley folks about exactly this question of how can we bring this method of this notion of formalism to the compliance problem and do automated checking over their software to really enhance their ability to have confidence in what it's doing. And as we were talking about this, we gave a couple small presentations at some workshops, and the folks in Goldman Sachs were really interested, and this was great. They said, we have the same problems too, and we need the same sort of pipeline for doing formal methods analysis. We have the same issues with managing a compiler, managing an IR, managing all this other stuff. And since we're all open source, can we come together and develop a shared infrastructure for managing this IR, managing the compiler stack, and managing this analysis pipeline and tool chain? And can we develop that in the open, right? And so that brings us to this Morpher platform, which we really started with what they'd done at Morgan Stanley, and then we've sort of iterated it to make it a nice shared artifact. And it has a lot of great features. It supports multiple language front ends. So, I showed a couple examples. Actually, the functional language that they were in is Elm. I mentioned that you can actually take Legend pure code and compile it into the MorphirIR. We're working on a front end for our experimental language from Microsoft Research here as well. It has several backends, so you can emit like Java bytecode, you can emit JavaScript, a number of other things, so it integrates nicely with existing tool chains. We're working on building out an integrated validation pipeline, and then it has some sort of nice AOP style injection for putting in like monitoring, logging, sanity check operations that are really important for anything running in this fintech space. Now, the thing that I really sort of came in and pushed on was it's already starting from this great functional core, but can we tweak it a little bit to make it sort of the ideal world for doing symbolic and formal methods type stuff? So let's get rid of all the things that you might have in like a JVM common bytecode or a CLR bytecode that make it really difficult to build scalable, precise analysis tools. So we made sure that the IR does not have any mutability, is a purely functional core. It has no loops, only limited uses of recursion. It's fully referentially transparent, fully determinized. So it's about the friendliest place imaginable to do, sort of analysis work, whether it's abstract interpretation, model checking, theorem proving, you name it. So the end is sort of a system that looks like this. Here's our surfboard example code that we saw before. And we're going to go and we want to run our checker on it. And we want to either prove for every error that it can't happen, or if it can happen, we want to actually generate a counterexample. So we take the Elm code, we compile it to the MorphirIR, we run the checker on it, and sure enough, we find out that there's a div by 0 somewhere in the code, and we produce an input that'll actually exercise that so we can go fix it very easily. And if we went and fixed it, ran this again, it would just report that there are no errors. So, how does all this sort of work? Well, here's kind of the system architecture of Morphir. So you can see that we have a sort of a front end that can consume multiple source languages, Elm, Legend, I mentioned. The Morphir core IR, which we'll go into a little bit more detail, which is kind of the place that we've worked to make everything scalable and everything work together. And then this validation pipeline on the left, which we've been working to build out in a way that you can plug different checkers. So this is actually a pluggable and extensible thing, and also set up in a way that is intended to make success easy. So if we can get a great result, we get it easy all the time. And also, if for some reason analyses time out, if they're incomplete, we can still always produce some actionable result for a developer, right? We don't want to have a system where if we aren't perfect, we fail catastrophically. We want to sort of degrade gracefully. And we'll talk about that a little bit more in a second here. So diving into what the MorphirIR looks like in a little more detail. As you'd expect, it sort of has the standard primitives like bools, ints, floats. From the fintech space, we also have a couple other types that are important and a little less common: nats, big ints, big nats, and decimals, which are really important for currency calculations. Data types has the standard tuples, records, and sort of classic algebraic data types. The containers is a space where we have lists, sets, and maps with a rich set of operations on them, right? And this is a place where, rather than having people write their own recursive traversals, we really want to have them fall back on a fixed set of library functions. And in order to avoid a lot of the problems that come up with equality and different versions of equality and needing to compute user-defined functions on equality and the problems that can cause in analysis, we restrict these only to use a set of primitive keys for like sets and maps. And then we have higher order functions, we make them parametric. So although they look like arbitrary lambdas, we syntactically set them up so we can always defunctionalize them. So the programs in the IR can actually be reduced to just simple first order function invocations everywhere, which simplifies a lot of analysis tasks as well. For expressions, the language looks very much like you'd expect the IR to look like for a let-bound language. So we have the standard set of arithmetic, comparative, and Boolean operations. Again, equality is restricted only to primitive values because we want to make sure everything's referentially transparent. Constructors, invocation is all pretty standard. Conditions, if then else's, cases, and then the standard let. So this is just a very simple core calculus and very easy to write the semantics for in whatever kind of analysis you want to do. So then the question is, well, how do you go and, what's the first analysis you want to write? Well, we wanted to go sort of big, and we wanted to say, we want to take this language and we want to convert it to SMT formula and just solve those directly, not try and do any clever, data pre-processing or incremental solving or modular analysis or anything. We're just going to dump the whole thing in the MorphirIR code, goes all the way to one big SMT formula. And this is actually pretty easy because the MorphirIR constructs are basically one-to-one with what exists in the SMT lib theories and language constructs. So nats and ints, we actually map to bit vectors. Big ints, big nats go to int. String goes to string. All the data types map easily into the theory of constructors. Functions, since they're pure, referentially transparent, everything goes very nicely to define fun. So if I wanted to compute have the min value function in Elm, and I wanted to translate it into the SMT formula that we're actually going to check, it is basically this, right? And you can't imagine a much cleaner, much simpler SMT formula for computing the min. It's basically what you'd write if you were to write it by hand in SMT-lib, and it is very well suited to efficient proving with a theorem prover like Z3. So this works really well for the core language. It results in very clean and easily solvable formula. Now, I did mention that since we don't have loops and recursion, we nudge people very much to use collection processing functions. So like map, filter, find index, all of this sort of stuff. And as you can imagine, this gets a little tricky because we, now need to decide how to encode these, and we'd like it to be a decidable theory, and we'd like it to be efficient. The nice thing is it's only a finite set of operations, so we can kind of do a clever encoding for each operation, and then we're done. We don't need to worry about a lot of problems with, say, loop invariance or doing inductive theorem proving. It's pretty much, a finite set of things we need to manage. On the downside, we're still doing reasoning over symbolically bounded length structures, so we can't finitize them directly. They're potentially infinite. So we have a tech report that talks about how we do this in more detail, but basically for the purposes of this talk, you can imagine we use, since our nats are bit vectors, then we can be clever with our quantifier introduction and make sure that all of these operations are in the theory of quantified bit vector formula. Now, you might go, oh, this is, if you have 64-bit ints, you have 64-bit bit vectors, and you have a bunch of quantifier nesting, does this scale? And I mean, even if it scales reasonably for, say, a couple thousand lines of code or 5,000 lines of code, is this going to scale for 10 or 20,000 lines of code? And so that brings us to the next thing. No, it doesn't scale infinitely. And so we build the checker workflow specifically to take that into account, right? Because in the ideal world, we'd like to always come back with sat or unsat on one of these formulae. Either the error is impossible, or here's a concrete witness input. But, if we have a 64-bit bit vector and a bunch of nested quantifiers, eventually the solver is going to time out. So as I mentioned earlier, our goal is to sort of embrace this. So we want to produce a great result as much as possible, right? We want to produce that sat and unsat whenever we can, and we built the language in order to make that as feasible as possible, the IR. But we also, when we can't, we still want to provide the developer an actionable result. And so we sort of have what we call a hierarchy of confidence boosting results. And so there's 1A, 1B. I either give you a proof that an error is infeasible, or I give you a witness that shows a debuggable input for that error. Now, it might be possible that I can't prove that an error is infeasible for full 64-bit integers. But, in our surfboard example, let's suppose that I make my bit vectors shorter. Let's suppose I make them so that I prove that as long as the request is for less than 4,000 surfboards, the error is impossible. Well, that's still a really valuable result. I mean, for that application, that's probably as good as proving it for the full 64-bit int space. But even in the case it isn't, that's still a very valuable result, that there's not some obvious flaw in your logic, right? That it's a very tricky case that happens later. And even if we can't prove for that, we can at least do an aggressive search of the search space, either via the solver or via fuzzing or other things, to give confidence that the error is not sitting there easily findable, right? These things are much deeper, and you can have more confidence in the quality of your software. So here's sort of a flow diagram of how that works. So the first thing we'll do is we'll encode the MorphirIR as an SMT formula with a small number bit width, maybe 4, right? And we'll see if we can prove that an error is infeasible or generate a witness. And we can incrementally make this larger and larger until we start timing out, or we've proved this for the full 64-bit space. Or if we can't, do the proof, if for some reason we keep timing out, we can try finding witnesses up at larger and larger spaces. So we can do small bit vectors, we can do small input list sizes, and we can iterate up in sort of an A-star search approach across the space. And this is very nice because it means that we can take sort of a simple solver that exists today, we can plug it in, and developers can start getting valuable results out of there day one, and they don't have to worry about debugging proof failure or anything else. Behind the scenes, we can keep improving our theorem prover technology, our encoding technology, adding new specialized checkers, and keep making their results better and better. And the developer's life just keeps getting better and better without them having to relearn this system every time we update it. So we really like this ability to sort of move forward effectively in the future. And that goes to our experience. So, we've been collaborating here on getting this core infrastructure done and doing this in the open source space. Kind of a couple angles that we've been working on is enabling multiple front-end languages. So Elm is the kind of the primary supported language here, but we also have front ends for Legend, and Bosky, this Microsoft language, is in progress. And then we've been doing some checking on sample applications to experiment with this checker pipeline and see what our experience was there. And we've been looking at both kind of these line of business applications I described, and then also working on some of this LCR app writing and checking components there. And we've had great results with this so far. In fact, we see very few timer timeouts, even though we're using bit vectors and floating point numbers and a number of theories. There are some places where it's slower, so it's great to see that when we do start timing out, we'll still have a nice fallback, but so far so good. So a couple of things that are interesting that we're really interested in hearing more about from the community is sort of how we can extend this and build this out in the future. And I want to call out a couple areas to collaborate. So one is sort of pluggable checking. Like, we built the checker pipeline. It's not highly coupled to a specific approach like SMT solving or abstract interpretation or anything else. We tried to make it in a way where you can plug in all sorts of different analysis and all sorts of different checkers. And one big opportunity there is then, rather than trying to just do a big hammer of a full SMT solver, can we plug in some lightweight checkers? Like, many of the things we're looking at are simple linear arithmetic relations, right? We don't need full SMT solving for that. Octagons or some simpler abstract domain would be really effective for many of these. And being able to do this in real time or near real time would be great for a developer experience. And of course, there are opportunities for more sophisticated reasoning as well. Like, recursion is part of the language. And right now we very crudely under approximate it, but having some support for inductive proofs or compositional inference would be a great advance in the system as well. One interesting thing is Elm does not have a lot of support for specifying user-defined assertions. So right now, most of the properties we've been checking are sort of core lib spec things. So division by zero, out of bounds, but we'd really like to add more user-provided assertions. So for example, like in the regulatory compliance, there are many cases where a number should not be zero, or you're going to take the max of some two numbers, and you'd like to be able to assert that overall some numeric relations are satisfied, even if they aren't precise. And there's just not a great way to do that in Elm. So we're looking at, how can you introduce some of these constraints? And, I mentioned data invariance specifically, or another example is you'll see code with a buy price and a sell price. They might both be decimal numbers, but they're not interchangeable. So how do you specify these sorts of relationships and type constraints in a way that's easy for a lot of less expert developers to use effectively, right? So this is a space where I think there's some really interesting possibilities to look at, how do you extend a language with specifications and contracts, and how do you make it, nice and easy to use here? The other one I want to call out is specialized checking. Right now, the solver we use is fairly generic, right? It knows about the numerics and all this other stuff, but it doesn't have a good insight into, let's say, numerical stability or divergence, right? Or sensitivity of various floating point algorithms. So this is an area where having a checker that's maybe specialized to look at some of these things would be really valuable. The other thing I want to call out that's huge in this space, and we really haven't had a chance to look at much yet, is PII and sensitive data leakage, right? These systems all consume vast amounts of data that is very sensitive, and they move it around. And we'd also like to be able to have assertions that certain data doesn't reach certain endpoints, and check this under various, degrees of sensitivity towards leakage. Everything from, the classic, does high value data reach a low value source, to some sort of like information theoretic, like, am I leaking some non-trivial number of bits on that data out, even if I'm not leaking the whole secret? So just in conclusion, like, I think this is a really exciting set of initial results. We've been collaborating both in academia and across several large investment banks to build this IR and shared stack. And I'm really excited to see a stack being built that takes making formal methods sort of a first-class citizen and a practical thing as a guiding principle, you know, that's baked in from the beginning rather than being bolted on as an afterthought. And I think it's amazing once you eliminate some of these huge problems that you experience when you're dealing with like Java bytecodes or anything else, that the opportunities it opens up to be effective in the analysis space. And also, I'm very happy that we sort of put some effort into the workflow design to make it consistently actionable and friendly for developers, while giving us a lot of headroom as we improve the state of the art and formal methods, that it sort of automatically and transparently improves the results that developers see. So, you know, I think this is an ideal opportunity for us to showcase the value of formal methods in software development. And I think it's a, you know, we have some partners who are really excited to benefit from the kind of, you know, results that you can get by taking not just a process-based approach to software quality, but actually having a real concrete formal definition of quality and being able to execute on that. So I just want to wrap up here with a couple links to the Morphir open source GitHub repo. So you can download that code, you can take a look at it. The liquidity computation sample that I mentioned, I have a link there. And then of course I have the tech report that talks a lot more about the details of how we do this container encoding and verification on that, if anybody is interested as well. And I think that kind of wraps it up for me. And I think I have a few minutes left over for questions. So happy to take anything. And I believe Stephen is here as well virtually. So if you see him around, you can certainly ask him a lot more details about the financial industry aspect of this.
Cool. Thank you for the talk. That sounds like a really exciting collaboration. Are there any questions in the room?
I don't see any questions yet.
Okay, so I have a question. So what is practically, do you think, like the biggest barrier to this becoming something that will be widely used in fintech? Is the barrier scalability of the formal methods, or is it a more of a kind of social problem, or sort of a kind of engineering, and like engineers needing to invest time in sort of setting up verification? Like what's going to have to change for this to become widely used?
Well, I think, you know, this is one of the things that really excites me, because the Morphir stack actually came internally from what Morgan Stanley has done. So it's actually used fairly extensively internally there. So for us, the big challenge really is just the engineering to integrate various checking tools into the pipeline, and then be able to assess how effective they are in, you know, detecting various issues, and then winnowing down and maybe building out a standard stack of this that they deploy internally, and then allowing other people to experiment with what they want. So, you know, I think we're in, you know, the barrier to adoption is actually pleasantly low in this scenario, as opposed to a lot of other projects I've been involved with.
Okay. So have you had non-expert and like non-expert users trying this out yet?
Yeah, we haven't had a deployment, you know, to a completely independent test set, shall we say. But you know, we certainly have had some people who are familiar with the project. You know, like like a good example is Goldman Sachs, right? Mm-hmm. They basically took an app, a very small app, ported it over, made sure it ran through the Morphir pipeline, hooked it up to the Bosky repo, and were able to generate errors, you know, with just a minimal amount of support from us. So that was a pretty nice result to see.
Okay, cool. Do I have time? I mean, are there any other questions? Otherwise, I have one more question that I would like to ask, which is how meaningful have you found this, like being able to say when a query has timed out? How does that actually give you useful information about the property you were checking, or does that just tell you that the solver you were using wasn't good enough this time?
Well, I think what it does is, interestingly, when I talk to developers, I go to a Node.js conference and I say, well, wouldn't you love to be able to verify that your software is correct, right? That it has no bugs. The response I usually get is, hey, if I want to fix bugs in my software, it's super easy for me. I have a GitHub repo full of bugs that I could go fix. So the problem for me isn't knowing which error and which bug, there aren't any of them. It's knowing which one to prioritize and where should I put my effort, right? And so I think the value that developers get from, let's say I look at an error and I say I've timed out repeatedly and I can't find any input that triggers this error. Then they can sort of take that and say, like, unless I have a reproduction in the wild that is very, high user impact, then I should focus my time on some of these other bugs where I know exactly what's going on and I know that they can be triggered very easily. So it's really, the value is in allowing the developer to triage and figure out where to spend their limited time, because they want to make great software, but they have limited resources to do it. So I think that's the value there, is even if we can't answer definitively about this bug, we can help them sort of prioritize and categorize how they want to think about it in their overall set of priorities.
Okay, that makes a lot of sense. Thanks.
Yeah.
Cool. Well, I think we've just filled up the time, so we should move on to the next speaker. But thank you for the talk. That was really interesting.
Great. Thank you appreciate everybody attending in person and virtual. Thanks.